So, good morning everybody. In the last session, we discussed the importance of the subject partial differential equation in the field of applied mathematics. And of course, as the topic assigned to me, I have already started the development of the heat equation right from the beginning of the 19th century, where the scientist Joseph Fourier derived the relation between the quantity of heat flow across conductive material, which is directly proportional to the temperature gradient. On the basis of that particular Fourier law of heat conduction, he developed the one-dimensional heat equation, and then we solved one boundary value problem, which is published by Joseph Fourier himself in the year 1822. So we have seen the solution of that particular problem with the help of separation of variable method, and surprisingly, I told you one important thing, that how he came across the expansion of arbitrary function fx in terms of infinite trigonometric series of a trigonometric function, and later on all of us is well known by Fourier series. Okay, so that part already we have seen. Now today, I don't know, I think it's still not working. So today I will show you the development of the heat kernel and its properties. Okay, so for the development of heat kernel, again I will consider one particular problem. Okay, here let us consider a rod of length L again. Suppose this is a rod, this is a finite rod. Okay, the length of rod is L, and now a little bit minor geometric change has been done over here, that this rod has been molded to a ring shape. That is, it has been molded to a this type of circular shape. Okay, and here of course now what will happen over here, a point on a circle can be expressed as theta equals to 2 pi x. As you know, this represents the circumference of the circle, and circumference is given by 2 pi r. Here particular point, basically it is represented by x. Okay, and therefore any point on the circle, it's a unit circle of course, and therefore this x varies from 0 to 1. So this rod has been molded to a ring shape or into a unit circle. Now the point on the circle is described by theta equals to 2 pi x, and our problem is now again txt, which represents the temperature at a particular point x at a particular time instant t. Okay, and here x is represented, in terms of theta. There's a relation between theta and x is theta equals to 2 pi x. Satisfies one-dimensional heat equation. Again, this is a one-dimensional heat equation problem. Okay, where x varies from 0 to 1, time variable varies from t is more than or equals to 0, and subjected to the initial temperature t of x0 is equals to f of x. So this is the problem under consideration. One slight change has been done over here in the yesterday's problem, that the rod has been molded to a ring shape. It is converted into a unit circle. That is only the change. Now here, due to change in geometry, our approach is little bit different. So method of the solution is again same. I will use the separation of variable technique. That is here, as you are aware that t is function of space variable x and time variable t, and therefore by the separation of variable I can write it as a product of some unknown function of x, that is f of x, and some unknown function of t, that is g of t, which is represented by equation 17. And that separation of variable technique, I will substitute this value in the equation number that is 16, one-dimensional heat equation. So I can reach to this particular equation number 18, right? And of course, again, as like yesterday's problem, here x and t are the independent variable, and therefore by the theorem on equal ratio they must be equal to some another constant. I will call it as a lambda. Now the important thing is that as the point described here, which is located on a circle, and therefore f is a periodic function of period 1. Are you agree with this statement? Because we have molded to this particular rod to a unit circle, and therefore the point located on the circumference of circle, of course, which is represented by x, I mean theta equals to 2 pi x, and therefore as f is a function of x, so f should be a periodic function of period 1. So I will take the advantage of this particular property, and instead of discussing all the possible cases like yesterday what we did, here directly I can write the lambda is equals to minus 4 by n square. Okay. So n is again a positive integer, n belongs to z integer, I can say any integer. Okay, and therefore once I decide the value of lambda, then f can be written as, because this is a second order differential equation, you know that basic theory, so I need not to go well in detail. If it is required, you please let me know, but this is a d square, of course, right? So this equation, how can we write this particular equation? It's a d square minus lambda of f of x is equals to 0. Lambda equals to this particular value has been chosen because of the periodicity, I mean periodic property of the function. Okay, and now by finding roots, I can write this complementary function, that is f of x. A and b are the unknown constant. E to the power 2 pi, root of this particular lambda is 2 pi I and x, and b into e to the power minus 2 pi I n x. So this is the way I can write the unknown function f of x, represented by equation number 19. Similarly, I can write the first order differential equation for the g of t. Okay, and therefore d plus lambda of g of t, d minus lambda g of t, I can write the equation like this. So d minus lambda g of t is equals to 0, that is d is equals to lambda, obviously I will get, and lambda is nothing but 2 pi I n, and therefore the value of function t, that is which is represented by g of t, I can take another coefficient c, e to the power minus 4 pi n square alpha t. Okay, so this is the way that I can write the function f of x and g of t. Now once I obtain these two functions,
sir, please explain again why f will be periodic.
Sorry, why?
Why f must be periodic of period 1?
Because f is a function of x, and x is the point located on the circumference of the circle, and point located on the circumference of circle must be a periodic function, because after one rotation it will come back to the original position, isn't it? And therefore the f is going to be a periodic function. It's a unit circle, therefore it's a periodic function of period 1.
Okay, sir.
Right?
Okay, thank you, sir.
Yes, yes. Yes.
Mumbai.
So general solution, again I need to combine these two solutions. Now here what will happen, instead of writing, I will just go back. It's not working. What happened with this? So as a product of these two functions, I will combine these two functions, right? And now here you can see what will happen over here.
Can you please?
One important thing I will do over here, as I mentioned that n is a positive integer. So here n is plus 2 pi I n x. This is minus 2 pi I n x. This is again n square value, and n takes all positive integers. So by taking the product of these two functions and combining all n, I can rewrite the solution in this fashion. Okay, instead of writing separately positive integer n and negative integer n separately, I can write it as a summation n running from minus infinity to plus infinity an e to the power minus 4 pi square n square alpha t and e to the power 2 in x. Is it okay? I have just combined, instead of writing separate n as a positive integer, n as a negative integer, I have taken this summation and n running from minus infinity to plus infinity. So it's cover positive part as well as negative part as well as n equals to 0. So all the possibilities has been taken care over here in the equation number 21. Now our aim is to find out again an, this unknown coefficient an. To find the unknown coefficient an, I will use initial condition, that is t of x0 is equals to f of x. So whenever I will substitute t equals to 0 in this particular equation, and then this value of the temperature T is nothing but f of x, and therefore f of x can be written as summation n running from minus infinity to plus infinity an, of course, and e to the power 2 pi n x, t equals to 0, so this value will be 1. Okay, now basically our aim is to find out the value of coefficient an. So an can be obtained as like yesterday what we did. I have taken the advantage of orthogonality property of trigonometric function. Here also I can take the advantage of orthogonality property of the exponential function. I can multiply both sides by a to the power minus 2 pi in x and integrate where x varies from 0 to 1, so integrate within 0 to 1. So that way also I can find out. Otherwise, actually the equation 22 is nothing but the complex form of Fourier series. This represents a Fourier series, and therefore an represents a Fourier coefficient, and value of the Fourier coefficient we have standard formula. So an is equals to 1 upon 2 pi, of course integration running from minus pi to plus pi f of x a to the power 2 minus 2 pi in x. This is the formula for the Fourier coefficient. Directly you can take the advantage of Fourier coefficient formula, or if you are not satisfied, or you are not aware of the Fourier series or its complex form, then what you can do, you can process like yesterday what we did, multiply both sides by a to the power minus 2 pi n x and integrate, then also you will get this particular value of the an. So equation 21 represents the temperature at any point x at any time instant t, where the unknown coefficient an is given by equation 23. So this is what again we solve this initial value. This is the initial value problem, okay? Because this problem we have the initial condition is only taken care. So this is not a boundary value problem. This is known as the initial value problem. So this is the solution of the initial value problem. Ahead of that,
sir, how we take such value of lambda? How we decide?
Lambda is designed because, as I told you, lambda is the unknown constant which represent a constant of proportionality. Okay, now here point x is located on the circumference of the circle, and as it is located, the circle is a unit circle. As it is located on the circumference of circle, the function, the corresponding function f, which is a function of x, must be periodic of period 1, isn't it? As the point is located on the circumference, it will rotate theta equals to 0 to 2 pi. After theta equals to 0 to 2 pi, this will start the another rotation. So again it will trace on the same path. Obviously the function is going to be a periodic function, and as it is a periodic function of period 2 pi, accordingly I have chosen value of lambda, that is 2 pi in. Okay?
Thank you, sir.
Yeah. Now, here we can observe, as f is the arbitrary initial temperature, so f must be a Riemann integrable function, because after all we will have to integrate it. So basic mathematical property should be satisfied by this particular function for the well-posedness of the problem what I explained you yesterday, and therefore f is considered to be a Riemann integrable function, and coefficient an is of course bounded as it is given by the infinite series, And how I can say it's bounded? Because the factor e to the power minus 4 pi n, I mean pi square n square alpha t, as t tends to infinity, this value tends to 0, and therefore this converges to 0 extremely fast. As t increases, this value tends to 0, right? And therefore ultimately what I can say, even the temperature function t of xt is represented by the infinite series, and it is both way infinite. N varies from minus infinity to plus infinity. Even though it is given by the infinite series, the function txt, I mean temperature function txt, is a convergence. Okay? And of course it's a twice differentiable because it satisfies the heat equation, one-dimensional heat equation, right? Now, to understand the more properties and in order to develop the heat kernel, what I am going to do here, I will consider this temperature function along with the unknown coefficient an as an integral function. Okay, so I will consider these two equations together and I will substitute this value of an over here. So this is what I am going to do. Now, for better understanding only, I have changed the variable, and as you are aware that in the definite integral, even though if we change variable, its value is same. The variable, for better understanding only and to avoid the confusion, I have changed variable x to y. So there should not be any conflict here over here. So I just substituted value of a n over here. This other term are as it is. Okay, and this integral equation along with the summation is rewritten 1 upon 2 pi. I can take outside integral function, as you know it's a linear, so I can take 0 to 1 f of y, and this summation is basically for n. So these terms I can shift it inside because integral is taken with respect to y. So there is no harm, there is no mathematical loss if we shift this term inside. Okay, because the one exponential function is function of t and other is function of x. Then I can combine this exponential function over here and I can rewrite like this. Now this equation 27 also represents a temperature function at a particular point x at a particular time instant t. But in another way, this can be written as a convolution of f and ht, where ht represents a heat kernel for a circle and heat kernel is given over here, this bracket term, that summation n is equals to minus infinity to plus infinity e to the power this time variable term, that is minus 4 pi square n square alpha t and a to the power 2 pi I n x. This is a variable ultimately, even though it is x. If you are not aware of the convolution of two functions, I will just write the definition of the convolution for your better understanding, and then I will go ahead. Suppose f of x and g of x are two functions. Okay, x is equals to suppose 0 to L, then convolution of f of x and g of x is denoted by f star g, and a is equals to 1 upon 2 pi integral 0 to L, whatever domain of x is there, and this is f of y, g of x minus y dy. So this is the definition of convolution of two functions. So here ultimately what we obtain, so this equation 27 is nothing but convolution of that initial temperature f of y, and of course this exponential term in t, and of course space variable x, which is also in exponential term. So this can be written as a convolution, and therefore the simplified form of the solution in terms of convolution of two unknown function is given by equation 28, where h of t, again I am repeating, this is nothing but now heat kernel. So this is how we have developed the heat kernel for the one-dimensional heat equation. If you have any doubt of this over here, you please tell me, otherwise I am going to the further properties of this particular heat kernel. Yeah, please.
So, we have taken alpha from where exactly?
Alpha is in one-dimensional heat equation itself. I will just, here it is. This is alpha. Alpha is the, yesterday we derived that one-dimensional equation. This is a standard one-dimensional equation. Whenever you are dealing with the one-dimensional problem, related to the finding out the temperature at a particular point, space variable and time variable. So you can consider this equation as a standard one-dimensional heat equation. Here alpha represents the thermal diffusivity. Okay, this is a physical property of that material. which the material under consideration, this is a physical property. Basically, thermal diffusivity is ability to store the heat within that particular heat conductor. And whatever domain X is, that you can take along with. Okay, so this is standard one-dimensional heat equation.
Hello.
Yes, yes, yeah, please.
Vinayak sir, good morning.
Yeah, good morning.
Sir, I have a very small question.
Yeah,
This
please.
convolution, what you have defined, is there any physical meaning of it? This looks, we always see either in the integral form or summation form convolution. There are two functions,
Yes.
f and g, we convolute in this way. But
Yeah.
how physically we can understand this?
Physical understand, actually this is a this is purely mathematical concept. Okay. This is not something like which is applied in a real life situation. This is purely mathematical concept, and this is for the simplicity only we are defining the convolution of function. Any physical meaning, if it is, I don't know exactly, but as per my understanding, this is purely mathematical concept. Okay, and this is used for the simplification, like right what I did right now.
Okay, sir.
Yeah. Just a minute. So here it is the solution of the temperature function in terms of convolution of the initial temperature F and heat kernel HT. Okay, and heat kernel HT is given by equation 29. This is what up till now we have seen. Now we are interested to find out the we study the more mathematical properties of this particular heat kernel, and of course accordingly then how it is helpful for the further understanding. I am coming to that particular point, but for that I need one or two basic definitions. So I will define square space. The square space on R consists of set of identically differentiable function f and all its derivative, that f double dash, f triple dash, and any nth derivative are rapidly decreasing functions. Okay, so this is where in the sense that if I take the supremum value x for the real, x is any real and mod of x to the power L, and any Lth order derivative of that is mod of fx, it's finite for every k and L positive. So this is nothing, only one thing you can understand over here. The intention behind including this particular definition, what I am going to do, I will take the advantage here, it's a rapidly decreasing function, and this is directly applicable to in my problem, because as I told you that e to the power lambda into suppose t here pi square t, where t tends to infinity, this value tends to 0. So this is rapidly decreasing. Sorry.
Maybe you use a black pen that is very light.
Okay, yeah, sure. Okay, so this is again a rapidly decreasing function, and therefore here I can use this particular concept. So that is the intention in behind including this particular concept of the square space. Okay, so and of course if you are interested, you can learn more about this particular space, because and square space over the real R is S of R. Okay, and it's basically it's a vector space over C. So my theorem is f belongs to S of R. Now I will, as I told you, I am going to directly consider f as a function in this square space. P of xt, which is already we have been derived that convolution of f star ht, that is f and ht for positive t, and ht represent the heat kernel. Then the statement of the theorem number 1, t is c square, is a twice differentiable function because it satisfies the one-dimensional heat equation. X is real, t is positive or more than equals to 0 also you can take. T solves the heat equation represented by, this particular expression solves the heat equations. Now t of xt tends to f of x uniformly as in x as t tends to 0. Hence, if we set f of x as the initial temperature, then T is continuous on the closure of upper half, Okay, so R2 plus its upper half, so it's a set of point order pair xt, x is R and t is more than or equals to 0. Okay, so and third is that, so if we consider the difference between t of xt and minus fx is a mean square function, of course. Okay, so integral minus infinity to plus infinity, t of xt minus f of x, absolute value and its square tends to 0 as t tends to 0. So these three conditions, basically what I want to say here, if f which represent in unknown initial temperature which belongs to this Hall space, and t of xt is represented the temperature at a particular any point x and any time instant t, which is represented by a convolution of f and ht. Okay, then it satisfies the one-dimensionality equation, it satisfies the initial condition, and of course the difference between that t of xt mean square value tends to 0 as t tends to 0. So this is particular theorem. I have not added proof of any theorem because we have a time limitation and we have to cover so many things within a short period. So proof is not added over here, but proof again we'll have to go more technical things, so that if you are interested later on you can refer many related book. I will give you a list of book later at the. Now one more concept I will add over here before going ahead. That's just now I taught you the heat kernel. Whenever we are talking about a particular kernel, this concept of good kernel plays a very important role. So let me explain what is this good kernel. Good kernel, it's a family of kernel k and x, n is equals to 1 to infinity or whatever. On the circle is said to be family of good kernel if it satisfies the following properties. A family of kernels satisfying 4 properties is known as a good kernel. What are those properties? Property number 1 is the positivity. For all n more than or equals to 1, k and x is more than or equals to 0. Second property, if I integrate k and x within minus pi to plus pi, 1 upon 2 pi into minus pi to plus pi, this integration is nothing but 1. Okay? There exists third property, there exists m positive chilling, such that for all n is more than or equals to 1, that integral minus pi to plus pi, absolute value of k and x dx is bounded by some positive constant that is less than or equals to m. And one more important property for delta positive, integration over this particular range, that is delta is less than or equals to mod x is less than or equal to pi, that absolute value of k and x tends to 0 as n tends to infinity. You need to understand this particular interval over here. If I plot a real line, okay, and I want just this particular integral, that is what is that, delta is less than or equals to mod x is less than or equals to pi. So if it is 0, then of course x is between delta to pi or somewhere here minus delta to minus pi. So this particular interval represent that delta is less than or equals to mod x is less than or equals to pi. Okay, so if a particular family of kernels satisfies all these properties, then we will call it as a good kernel. Because we are mathematician and we are very much interested, everything need to be well defined. Otherwise, in general, good and bad is not well defined. Okay, so here it is well defined. A family of kernels satisfying all these properties, we will call it as a good kernel. Okay, so I will go ahead with these two concepts. Now my point is the hit kernel is good kernel for t as t tends to 0. Already I have defined hit kernel. We have derived the expression for the hit kernel, and hit kernel is a good kernel. It satisfies all the properties whatever I mentioned in the last time. Okay, as t tends to 0, hit kernel is a good kernel. And what is the advantage to have all these properties of the good kernel? This is the advantage. You look at this next term. The next theorem, that family of good kernel, that is k and x n equals to 1 to infinity. It's a family of good kernel. F is integrable function defined on a circle. Everything we are defining on circle because I want to say that the f is periodic function of period 2 pi. Define on circle itself represent the property of periodicity of period 2 pi. That's the reason every time the geometry under consideration is circle. There is no any other intention. The intention is very clear. Before every time we are talking about this circle, circle, circle. The reason is very clear. I want to say that the function defined or this particular geometry is a periodic of period 2 pi. Okay. So then what will happen over here? If it is a family of good kernel, then as n tends to infinity, the convolution again f star kn x tends to f of x. As n tends to infinity, this convolution tends to f of x. So this is the advantage to have these properties of the good kernel, and directly I can take this particular advantage, and this will helpful for the convergence of that infinite series. So that's the reason I have included this concept of the good kernel. So f is continuous. Of course, this will happen whenever f is continuous, and if f is continuous, then this limit is uniform. Okay. So these are fundamental properties of the mathematics. Now here, as ht, that's a hit kernel is a good kernel, ht tends to 0, and therefore if I take limit t tends to 0, f star ht, which represents the temperature function, which is already we have seen. So this is equals to f of x, and therefore I can say that this particular convolution of f and ht satisfies the initial condition f of x. Okay, so this is the development of the hit kernel, and the property of the hit kernel, it's a good kernel, and as it is a good kernel, so I can take the advantage of this particular theorem, and I can reach to this particular statement that limit t tends to 0, f star, that is one of the statement what I mentioned in the last theorem. Here directly we can prove, or this is only the proof of that particular statement, that it satisfies the initial condition. Twice differentiability, you can easily check it. And that mean square value also, you'll have to do some mathematical simplifications, and you can easily reach to that particular statement. Okay. Okay, next slide. One more before going ahead, of course, as we are talking about the well-closed problem and everything, so of course I will just mention the theorem of existence and uniqueness. Okay, and here f is integrable function defined on circle. Once again, as I told you, we are considering a periodic function of period 2 pi, and therefore function is considered on unit circle. Then the function t defined on unit disk is given, this is known as the Poisson integral formula. Okay, the t of xt, this is already I have derived f star htx, and having these following properties. Property number 1, t has a two continuous derivatives in the unit disk, satisfies the heat equation. Okay, t satisfies the one-dimensional heat equation. Number 1 property, at the point of continuity x is any point of continuity, then t satisfies the initial condition, that is t of xt as t tends to 0 is f of x. If it is continuous, then limit is uniform according to that theorem on the good kernel. Okay, and if f is continuous, then t of xt is the unique solution of the heat equation. As I told you, I have not added the proof of any theorem to save time. So this is the theorem which will give you existence and uniqueness of the solution of one-dimensional heat equation. Up till now, if you have any doubt, you can ask me. Otherwise, I will go to the unbounded domain then. Up till now, we have seen a bounded domain. X belongs to 0 to L. Okay. Now we'll go to the unbounded. What will happen if x ranges from minus infinity to plus over real line? So here heat conduction in an infinite rod. Now rod is there again, but only the change is that here the length of rod is infinite. Its x ranges from minus infinity to plus infinity, whole real line. So the basic assumptions made over here, the position of rod coincide with the x-axis. The geometry you can better understand. Again, one-dimensional rod. Multi-dimensional I will go later on. Okay, it's a one-dimensional rod. It coincides with the x-axis. Okay, it's sufficiently thin because everything, as you are aware that we need to define each and everything. You cannot call this particular rod is thin or another particular rod is thick. So we cannot call it thin or thick at random. So thin and thickness is also the well-defined term as far as in this particular field is considered. So thickness, if this diameter is less than 20% of the length, then we will call it as a thin. The diameter of this particular rod, if it is less than 20% of the length, then we will call it as a thin. Okay, so rod under consideration is thin, and therefore we can analyze one dimensionally only. Otherwise, I will have to consider that radial direction and its thickness and along diameter. So many other physical parameters will come in the picture. That type of problem also can be done, but right now this is just initial stage, so we are discussing one-dimensional problems only. So it's a thin, okay, heat is uniformly distributed over a cross section at a given time instant t. Surface of the rod is insulated. Surface of rod is insulated means there is no heat exchange within this particular circumference and surrounding media. Insulated means not heat exchange within the outer layer of the rod. And uxt represents the temperature at the point x at the time instant t. So problem is again to determine temperature u at x and t. So this is the problem under consideration. Everything is exactly same. Only as I told you, the dimension now change. It's ranges over t. So again, as it's a one-dimensional heat equation without internal heat generation, as I told you, the property basically the heat conduction problems are classified again two particular parts. Is one is within internal heat generation and without internal heat generation. If there is no heat generation within this particular, I think yesterday I explained these things. So this one-dimensional heat equation is applicable over here. So this is one-dimensional heat equation. Now look at this: x ranges from -infinity to +infinity. T is more than or equals to 0, and the boundary condition, the initial temperature of the rod is f of x again, which is arbitrary unknown function, okay, and f is bounded, okay, and continuous. This is the essential condition I will have to consider because this is the mathematical requirement of the problem, okay. And another important thing, as I told you, the rod is thermally insulated. There is no heat exchange within this circumference of the rod into the surrounding media, and therefore I can add this particular property that u and u of x is tends to 0. There is no heat exchange, means rate of change is 0. Rate of change is 0 means ux is 0. No temperature loss is there, and mod x tends to infinity. Okay, so this is the mathematical formulation of the particular problem. Now we are going to solve this particular problem. Now here I cannot use that separation of variable method because x ranges from -infinity to +infinity, and this will create a lot of problems. As I told you yesterday, the separation of variable is not applicable all time. So it has many limitations. So here I cannot use separation of variable. So I am going to use integral transform technique. I don't know how much amounts you are aware of the integral transform techniques. Therefore, little bit I will talk because otherwise this will totally divert this particular topic. Little bit I will talk about the integral transform. What is integral transform? And then I will start actual mathematical procedure of solving this particular problem. So what integral transform does over here? Okay. So look at this flow chart. This is original problem. If I apply integral transform on this particular original problem, then problem is shifted to the transform space. Okay, this is original problem. By applying integral transform, problem is shifted to the transform space. Whatever space is there, according to what type of integral transform you are considering, accordingly this problem will be shifted to that particular space. Then this shifted problem to the transform space is relatively easy to solve. Basically, it's very difficult to find the direct original problem and direct solution of the original problem. It's difficult sometimes, and therefore I can take the advantage of the integral transform. I can shift the original problem into the transform space via integral transform. After shifting into the transform space, the problem is relatively easy to solve. how it is that you can see you can see in the solution, okay? And then finding the solution, that solution you will get in the transform space. You will not get solution in the original. Our original space now here, the original problem is txt, okay? Txt. So our space is means xt, space variable x and time variable t. So after applying transform, integral transform, this will separate to some another space. Either I will apply integral transform with respect to time variable, or I will apply with respect to space variable. Here I am going to apply with respect to space variable, because space variable x is ranges from minus infinity to plus infinity. So I am going to apply a Fourier transform. And after applying Fourier transform, then I will have to use some another variable. I will call it as alpha. Then x will be shifted to another variable, Fourier transform parameter alpha. T will be carried forward as it is. Okay, so this is our transform space. Xt is the original space, alpha t is the transform space. Okay, and then after transforming to the transform space, problem is relatively easy to solve. Okay, so I can find its mathematical solution, but the solution obtained is in the transform space. The solution will be is in alpha t, not xt. So I will have to convert it again alpha t. So for that I will have to apply inverse transform. Once I applied Fourier transform, I will get the solution in alpha t form, but I want to shift it into xt form, so I will have to use F inverse. So integral transform, simultaneously we will have to use these two steps, and then inverse transform. Okay, so this is how integral transform works for the solution of partial differential, ordinary as well as partial differential equation. Now, as I told you, I am going to use the Fourier transform. So first of all, let me tell you the basic definition of the Fourier transform, and then I will apply it. This equation 36 and 37 represent the Fourier transform and its inverse. Fourier transform parameter, I will take it as alpha. The Fourier transform is an integral transform which is given by this integral equation 1 upon root 2 pi integral minus infinity to plus infinity f of x e to the power minus I alpha x. This e to the power minus I alpha x is known as the kernel of the integral transform, kernel of Fourier transform. Okay, so this is a kernel of Fourier transform, and of course you can see in the inverse transform, as it is a minus alpha I alpha x, as in order to nullify this the effect of this particular kernel, in the inverse transform we can see it is e to the power plus I alpha x. Okay, and then f of x will be shifted to f of alpha after applying Fourier transform. Okay, and then f of alpha will be shifted to f of x by applying inverse transform. So these two equations explain the definition of Fourier transform and inverse Fourier transform. I am going to apply this particular Fourier transform. I will not go more detail. There are so many properties of the Fourier transform, and again mathematical properties and all those things. So this is that will be a different topic. Okay, I will directly apply over here. What is my original equation is ut is equals to k u x x. This is my original equation. This operator f is nothing but Fourier transform operator. So f is applied over ut, f is applied over whole equation, I mean to say. Okay, so here it is. I will denote, as I told you, we are applying Fourier transform with respect to space variable x. The variable under consideration, the independent variable, what plays role in this particular problem is x and t. So as I am going to apply with respect to x, the t variable will be carried forward as it is. There is no effect on variable t. Variable v will be carried forward as it is, even though if I apply integral transform. And therefore, the integral transform, I will just denote by a particular notation, integral transform of temperature u at a particular point x at a particular time instant t is denoted by capital U. As I told you, we are applying transform with respect to x, therefore x will be shifted to the Fourier transform parameter alpha at that time, in this process t will be carried forward as it is. So this is notation that we are going to use.
Okay, these are the notation that we are going to use. Okay, so what's next?
Any question? Okay. So you understand, even though if you are not aware of the integral transform, I think some means little bit at least outline you can better understand what exactly we are going to do over here. Okay, so I will go ahead now. So with these two equations I will go ahead. I am applying, let me again tell you, I am applying Fourier transform over the equation. Okay, and at that time the application of Fourier transform, this small u will be shifted to capital. This is just a part of notation. X will be shifted to alpha, t will be carried forward as it is. Next. I have written each and every step for your better understanding. Now here, actual definition of the Fourier transform I told you. What is that definition? 1 upon root 2 pi integration minus infinity to plus infinity. The function under consideration is ut, right? And e to the power minus I alpha x dx. I am applying Fourier transform on ut. That is derivative of u with respect to t. E is equals to k times 1 upon root 2 pi minus infinity to plus infinity. That side I am applying Fourier transform on uxx e to the power minus I alpha x dx. Now, as I told you, I am not going to do any change on variable t, and therefore this is a Fourier transform of ut. That is what I can say only over here. So small ut, I will write it as a capital ut. Capital ut represents the Fourier transform of derivative of u with respect to t. Because we are applying Fourier transform with respect to x, so this just I will write the notation wise. But here I will have to simplify each and everything because our Fourier transform is with respect to variable x and these derivatives are also with respect to x. So I will have to simplify each and every step. So I am going to apply integration by part. So k 1 upon root 2 pi is the constant. Okay, integration by part. I will write this exponential function as a first function and uxx as a second function because derivative is with respect to x, integration is also with respect to x. So this will be better for the integration purpose. So the integration of the uxx can be written as ux. I can reduce derivative by order 1. So ux e to the power minus I alpha x, limit is minus infinity to plus infinity, minus integration of integrated function and derivative of first. This is simple formula of the integration by part. Now what will happen according to our boundary condition, as per our assumption there is no heat loss, means rate of change of temperature, that is ux tends to 0 as mod x tends to infinity. This is nothing but mod x tends to infinity because x tends to minus infinity as well as plus infinity, and therefore because of this particular condition this first term will vanishes, right? Both way, as x tends to minus infinity this value tends to 0, x tends to plus infinity this value tends to 0, and therefore this first bracket will vanish. The remaining expression is this. Okay, now once again I am going to apply integration by part on this particular equation. Now what will happen over here, this I alpha I will take outside as it is a constant material property. 1 upon root 2 pi also I can take outside, and again the integration of ux can be written as u. I can reduce the derivative by 1 for finding integration e to the power minus I alpha as it is, and minus integration of integrated function into derivative of first. That way I can process here again. Again what will happen, our property equation number 35 tells us u and ux tends to 0 as mod x tends to infinity. Therefore again this first bracket will vanish. Okay. So first bracket will vanish. Okay, so remaining expression is like this. This is the remaining expression. But what is this remaining expression? You can see this k I square is minus 1, it's complex I, alpha square I can write, and this remaining expression is nothing but Fourier transform of u according to the definition, original definition of Fourier transform. So this you can see, what is this? This encircled thing. This is nothing but Fourier transform of u, and Fourier transform of u I can write it as a capital U. Okay, so this is the resulting equation. And as I told you, after applying the integral transform on the original governing differential equation or partial differential equation, now that partial differential equation is converted into ordinary differential equation with respect to single variable t. This is just an ordinary differential equation. I can solve it very easily. What I claim at the beginning, After transforming on the another space, the problem is relatively easy to solve. Now this is relatively easy to solve. Okay, and therefore you can see here, this is the ordinary differential equation. I can use operator D, where D represents d by dt over here. So d square k alpha square u. So this is the ordinary differential equation which can be easily solved. Next, and whose solution is given by this particular thing. Okay, as it's a single root alpha square k, so I can write it here. A alpha is a unknown coefficient, as like your constant coefficient. Okay, so again our job is to find out value of A alpha. Now how can you find A alpha? For that I have initial condition. What is that initial condition? Initial condition is nothing but u of x0 is fx. Okay, so here how can you find A alpha, value of A alpha? If I put t equals to 0 in this particular equation, after substituting t equals to 0, I will get u alpha 0 is A alpha. So I am interested to find u alpha 0. How can you find u alpha 0? U alpha 0 can be found out by applying the Fourier transform. We have applied Fourier transform on the original governing differential equation. At the same time, I cannot ignore the conditions given. So condition given is the initial condition. So on initial condition also I will have to apply Fourier transform. So here I am going to apply Fourier transform over this ux0 and Fourier transform over f of x. So let us solve this one and then next. So this is a Fourier transform operator ux0. ux0 is Fourier transform is nothing but u alpha 0 as per our notation. Okay, according to the definition, it is 1 upon root 2 pi minus infinity plus infinity ux0 e to the power I alpha dx. Okay, now here what is value of ux0 according to the initial condition? Ux0 value is nothing but f of x. And now again this equation represents a Fourier transform of f, and Fourier transform of f I can denote by f alpha, and therefore what I got, that is the Fourier transform of ux0, that is u alpha 0 is nothing but A alpha is nothing but f alpha. I can substitute in the last equation, and what I got, u alpha t is equals to f alpha e to the power minus alpha square kt. This is the solution of the problem, but this solution is in the Fourier transform space. This is not in terms of xt. Therefore, in order to find the solution of this particular problem in xt domain, I will have to apply inverse Fourier transform. Next. So to apply inverse Fourier transform, now this f inverse operator I will apply on the both sides of the equation. Now here, what will happen here? That is f inverse of capital U alpha t, directly as notation wise I can write u xt. But here again, this is a product of two functions. F alpha is a separate function, e to the power minus alpha square kt is a separate function. If I apply the operator f inverse on the product of function, the property of Fourier transform is that I can apply it separately, but I will have to take their convolution. Okay, so if I apply f inverse on f alpha separately, if I apply f inverse on e to the power minus alpha square kt separately, then it works. I can take it separately, but I will have to take their convolution after finding what I can say inverse Fourier transform. Now out of that, the inverse Fourier transform of f alpha is capital f alpha is fx. This is just a part of notation again. F alpha is fx. Okay, because we have written Fourier transform of fx is f alpha. Okay, and here directly I have written this because I skip, because this is a part of again a Fourier transform. How to find the Fourier transform of this exponential function is the part of Fourier transform, and it needs computational skills in the Fourier transform. So I skip that part also over here. Okay, directly I have written its Fourier transform. If you calculate, you will get this particular quantity, 1 upon 2 root kt e to the power minus x square 4 kt. Okay, so I got Fourier transform of first function as well as second function. I will substitute over here, but direct product is not our solution, their convolution is our solution. Next. So here I have written the convolution of these two particular function is solution. Again, this can be written in the form what I have told you in the last few slides. This can be written in the form of f star ht. Okay, What is HT? HT is the heat kernel. Heat kernel for this particular problem. Now heat kernel for this particular problem is given by this particular quantity. This is the heat kernel for this particular problem we have developed, and the solution is written again in the form of F star HT, and again as it is written, as it is a heat kernel, all the properties what I have shown you in the last few slides. It is a good kernel as t tends to infinity, and it is a good kernel. It satisfies all those properties of the solution of the heat equation, one-dimensional heat equation, and satisfies initial condition, and that mean square value tends to 0. All those properties are directly applicable over here. So separately, I need not to check is well posedness of the problem. The problem is well posed because it's a heat kernel and which is a good kernel, and the properties are directly applicable. Therefore, this is the one advantage to have in this particular form. Okay, and then as you know, the convolution of the two function is written in this particular form. F of x star g of x is 1 upon 2 root 2 pi minus infinity plus infinity. I can take any parameter that is x xi and g of x minus xi. So I will just substitute over here. So this is f of xi, and here x need to be replaced by x minus xi. So this equation 42 will give me the solution of the temperature at any particular point x at any particular time instant t. Okay, so this is the temperature within an infinite rod, which is obtained by what I can say using the integral transform technique. If you have any doubt in this particular method of solution, you please talk to me. I think it's already 10:36. So yes. So let us have a break for 10. Okay. Okay, what your according to your timetable? So okay, so this is a problem in the unbounded domain. Now let us go ahead. Only the one important thing I would like to share with you people as far as integral transform is concerned. You might have studied Laplace transform, basically Laplace transform, Fourier transform and all those things. So let me tell you one important thing over here. As our variable x was ranges over minus infinity to plus infinity. So Fourier transform was only applicable over there. You cannot use the Laplace transform or something like because Laplace transform is the most suitable transform for time variable, because t is more than or equals to 0. Okay, so t ranges from 0 to infinity. Therefore, for time variable, you can use Laplace transform, and accordingly you can solve that second order differential equation in x. So you will get solution. But as far as space variable x is concerned, so you will not use Fourier transform only because that is the most suitable and convenient transform for the space variable x, and particularly when ranges over R. Here as a special case only I have added one thing, that k equals to, if I write k equals to 1 and f of x is a fixed function, that is a is any constant for whenever x is positive and 0 whenever x is less than or equal to 0. Then our corresponding solution, that 42 becomes this way. So I can express 42 here because f of x is now constant represented by a. Okay, and here I can solve. You might be thinking that the temperature is in terms of integral function, so how can we determine a particular value of the temperature? But you must not forget that our initial temperature is again an arbitrary function of x. If it is a particular function, then you can solve ahead of that. Okay, so here in order to solve for this particular integral, you can substitute that eta is equals to this particular xi minus x upon root 2 root t, and then we can solve further integration by taking the advantage of the error function. because this particular integral represent the error function of x upon 2 root t. Okay, what is error? Error function is again a special function which is given by 2 upon root pi and 0 to x e to the power minus eta square d eta. Okay, so if we compare this definition of the error function with this particular integral equation, then we can see that this particular integral represent the error function of x upon 2 root t. Okay, so this is the way that the resulting integral and equation also can be solved if the particular value of f of x is given. Okay, so this is just the illustration I have added over here. Go ahead. Now, up till now, we have seen one-dimensional problem, bounded and unbounded domain. Okay. Now, let us go ahead and let us see multi-dimensional problem. What will happen? Two-dimensional, three-dimensional problems are there. So here, first of all, let me derive the equation of, generalized heat conduction equation, its boundary condition, and then let us go to the multi-dimensional problem. So for that purpose, here now I will consider a small small volume V and its corresponding energy balance equation with the physical properties like specific heat capacity and its density. So energy balance equation, how can you write the energy balance equation for this particular problem? So rate of energy storage in V, rate of heat entering in V, and rate of heat generation within that volume. If this is a particular volume under consideration, okay, and if I want to write the energy balance equation for the heat energy, okay, then what I will have to consider? I will have to consider the heat energy entering within this particular volume through the bounding surfaces. These are bounding surfaces. So from where the heat energy is entering into this particular solid. This is number one source of energy. The another source of energy is that this is known as the internal heat generation. As I told you, the problem of heat conductions are basically related to internal heat generation and without internal heat generation. So there may be internal heat generation, like example yesterday I have given you the piston of motorbike, there is an internal heat generation. So I will have to take care internal heat generation, number one, and heat energy entering through the bounding surfaces, number two. So combining these two will give me total heat energy within this particular volume. Okay, so this is the energy balance equation. I will calculate all these three and then I will substitute, and I will by simplifying I will get the corresponding heat conduction equation. So let us think one by one. So rate of heat energy storage within the particular volume. So how can we calculate it? As the volume V is the small volume under consideration, so total volume I will have to integrate over V. It's a volume integral, okay, and then specific heat capacity into density into rate of change of temperature with respect to T. Here T is the function of position vector R and time T. Here R represent, it's now a multi-dimensional variable, okay. So this equation will give me the rate of energy storage within that particular volume. And as it is a volume integral, I will have to consider volume integral, it's a triple integral, you know it. Okay, now Cp is the specific heat capacity and rho is the mass density of the material. Now the heat entering through the small area, because even though this volume is under consideration, its surfaces having this surfaces can be represented. So heat energy entering through the bonding surfaces, I will have to consider this particular area of this particular surface. Okay, so that area under consideration, a small area of course under consideration corresponding to the small volume V is represented by dA on the bonding surface, and this is nothing but the quantity of heat flux applied on that particular surface. So quantity of the heat flux as I told you yesterday, this is the rate of change of temperature with respect to that particular space variable. Okay, and minus sign is always there because heat flows from higher temperature level to lower temperature level. So heat flux entering through the bonding surface is nothing but minus Q bar is a vector quantity, R bar, T bar, and U is the outward unit normal on that particular surface. Okay, so this is the heat energy entering through the surface, bonding surface I mean to say. Now I will use the basic Fourier law again. The Fourier law, yesterday we discussed this Fourier law. okay, the relationship between the heat flow and the temperature gradient. The heat flow is directly proportional to temperature gradient that we have already seen. So here, what I can write here, the rate of heat entering through the V, I mean this particular volume V, is nothing but I will have to integrate over surface under consideration. Okay, this is the surface under consideration. So I will have to integrate over A, means this is the surface area. Okay, and Q bar dot U bar, and this Q bar can be written as per the Fourier law of heat conduction is the temperature gradient, or I can write it as a divergence quantity. Okay, by using the Gauss divergence theorem, I can write it as Q bar dot U bar is nothing but it's a divergence of Q bar. This is the Gauss divergence theorem from the vector calculus. Okay, U is the unit vector. And now the heat generation, the total, if G represents the heat generation within the small volume V, so total heat generation within that volume, again I will have to integrate over a volume V. So I got all these three quantities, the rate of heat generation within the volume, heat entering through the surface area, and total heat energy. I got all these three quantities. So substituting these three quantities in the energy balance equation, I will get this equation number 47. Okay, so this equation 47 represents the energy balance equation for this particular problem. Now, this volume V under consideration is very small, and therefore I can remove the integral. Okay, and therefore the corresponding equation can be rewritten in this particular form. And one more substitution I can do over here, that the quantity of the heat flow, I can write it as a temperature gradient by using the Fourier law of heat conduction. And therefore this Q bar I can write it as a minus K delta T. So this is the governing partial differential equation, heat conduction equation, generalized I can say, for the multi-dimensional problems. Okay, so I can simplify further, and I can take the relationship between the thermal conductivity and thermal diffusivity and all those things. So equation can be written as like this. Now here you can see this first part is same as like the one-dimensional equation, rate of change of temperature with respect to time 1 upon alpha. The del square also, as far as one-dimensional quantity is concerned, del square I can write it as a second order derivative of temperature with respect to variable x as far as one-dimensional quantity is concerned, right? And this quantity, this third term represents a rate of heat generation within the volume under consideration. Rate of heat generation within the volume under consideration. So this particular quantity, this first two term as same like one-dimensional heat equation. Only here del square is written, and del square represents it's a Laplacian operator, of course. Okay, so this is also a Laplacian operator for one-dimensional equation. Okay, and this is the rate of heat generation within that particular volume. Alpha is the thermal conductivity of the medium, and the thermal conductivity, how it is related with the thermal diffusivity, that alpha is equals to kappa upon rho Cp. So this is the relationship between alpha and kappa. Okay, so this is generalized heat conduction equation for multi-dimensional problem. Now it's coming to the special cases of this particular heat equation. Now, as I told you, in some heat conduction problem there is an internal heat generation. In some problem there is no internal heat generation. If no internal heat generation problem is under consideration, then of course this G R bar T is going to be a 0, and the resulting equation is like this. So this equation is known as a Fourier heat conduction equation. Yesterday only we derived for one-dimensional case, and this is a well-known Fourier heat conduction equation, and this is applicable for no internal heat generation. Now second, when steady state temperature conditions are there. Steady state temperature condition when temperature is independent of the time. Rate of change of temperature is 0 with respect to time. If temperature does not vary with respect to time, we used to call it as the steady state. Okay. Otherwise, the temperature is known as a transient temperature. If temperature varies with the time, this is known as a transient temperature. So if steady state temperature conditions are under consideration, then rate of change of temperature with respect to time, that first term will vanish. Okay, and the resulting differential, there is no time variable now. Here T and G is function of R, space variable R only. So this is known as the Poisson heat conduction equation. And the third condition, steady state with no internal heat generation. Steady state means again temperature is independent of time, and no internal heat generation means G term is also not there, because G represents the internal heat generation. So resulting equation is del square T is equals to 0, and this is nothing but a well known Laplace equation, and this represents a steady state temperature conditions. Okay, so these are few special cases of generalized heat conduction equation. If you have any doubt in this particular derivation or in special cases, you please talk to me. Otherwise, I will come to the boundary condition. As I told you, boundary value problem consists of governing differential equation as well as boundary conditions. Now let us talk about generalized boundary condition. Up till now we have seen very basic boundary conditions, or something like temperature prescribed boundary condition. But in the actual real life problem, we will come across the many different physical situations, and we will have to interpret in the language of mathematics. So basically the types of boundary condition is classified into 3 types. Number 1, the temperature prescribed on a particular boundary is a function of some unknown function of position and time. Here you can see T is a function Fi, because that particular boundary surface, because it's a multi-dimensional problem, so boundary Si is under consideration. So T is a function, some unknown function Fi, which is a function of position R and time T. Okay, so this is directly temperature is prescribed on a particular boundary surface. This is known as the first kind boundary condition, or otherwise you can call it as a derivative boundary condition. Temperature prescribed on a particular surface, which may be constant, which may be function of position, which may be function of time, which may be function of both. All possibilities are open there. Which may be 0 also, 0 temperature condition. That time we will call it as a 0 temperature condition. Like yesterday in the first problem only we have seen that 0 temperature condition. The second is known as second type boundary condition, or Newman boundary condition. What is this Newman boundary condition? Newman boundary condition is not only temperature but rate of change of temperature. The rate of change of temperature, which is a function of some unknown function f, which is again f is a function of position and time, or sometimes only position, sometimes only time, sometimes both, sometimes constant. All possibilities are open there. So this is a second kind boundary condition. We used to call it as a second kind boundary condition, or another way we will call it as a Newman type boundary condition. So this is the rate of change of temperature prescribed. As I told you, this is in the physics language we used to call it as a heat flux. Heat flux is prescribed on a particular boundary surface. And if this is 0, that is rate of change vanishes. What does this mean? That there is no heat exchange, there is no loss of heat. And just now I have seen one that infinite dimensional problem where we have seen that property, that Ux was 0, that is the rate of change of temperature with respect to variable x was 0. It means that surface was insulated surface. Technically we can call it as a insulated. Insulation means there is no heat exchange within the surrounding media. This is second kind boundary condition. And third is Robin type boundary condition, or we can call it as a third kind boundary condition. The third kind boundary condition is a linear combination of first two. What is first? First is simply temperature prescribed. Second is rate of change of temperature. Okay, and third is linear combination. Here of course I will have to take some unknown constant ki and hi over here. So this linear combination, which is again an unknown function of position and time. Okay, so this is known as the third kind boundary condition. Now this third kind boundary condition also sometimes, if this is equals to 0, then this is known as a homogeneous boundary condition of okay, and actually this is nothing but Newton's law, because if I shift this term over here, sometimes what will happen over here? So this will give you the rate of exchange of the temperature, as I told you yesterday, that conduction, convection and radiation. Once this body is heated up, then this will start to convect, heat convection within the surrounding media. So rate of convection can be calculated with the help of this particular boundary condition, because what will happen over here, the surrounding temperature I can represent by Fi. The temperature prescribed, of course, over here, that is a T, and then rate of change of temperature can be written difference between that Fi and T. Okay, so this is nothing but this will represent, this will give you the rate of convection within that particular boundary surface. So these are basically three type of boundary condition used in the heat conduction equation, boundary value problem of the heat conduction. Okay, so these are basically three types. So this is about the generalized what I can say, the heat conduction equation and generalized boundary condition. Now as I told you, up till now we have seen one dimensional problem only. Now I will go to the multi-dimensional problem. Now we'll shift R to direct now Rn. Okay, so here the domain is now Rn from 0 to infinity. Rn for space variable and 0 to infinity for time variable. That's why domain under consideration is Rn for 0 to infinity. This is for space variable and this is for time variable. Now the problem is same here. This is the rate of change of temperature with respect to time variable, and del is the Laplacian operator, as just now we have derived the generalized heat equation. So del represents the Laplacian operator. Okay, so this will give you, if it is in particular also I can tell you for the better understanding. If we are working in the Cartesian, three-dimensional Cartesian domain, so then this del is nothing but this our Laplacian, this operator. Okay, this is del operator in three-dimensional Cartesian domain. So how can you write this particular equation? So this particular equation is rate of change of temperature with respect to T is equals to del applied on the temperature function u. Here 1 by alpha I can take it as a coefficient, otherwise we can take it as a 1 also, no problem. This thermal diffusivity coefficient. Okay, so this is the generalized heat conduction equation. Del I have written because not necessarily every time we are working in the Cartesian domain only. Sometimes it can be cylindrical, it can be spherical. Accordingly, del operator I will have to change. Okay, so our aim, and again this problem are subjected to non-zero initial condition that u of x0 is f of x. So again this problem, as the domain under consideration here, it's an infinite domain, and therefore I will use Fourier transform in its inverse. The same technique what we have used, only the thing is that here operator del, it's a now multi-dimensional operator rather one-dimensional operator. So Fourier transform, already I told you the definition. Here I have considered xi as a Fourier transform parameter. This is given by equation number 50, and which I can write it as 1 upon root 2 pi minus infinity integral minus infinity plus infinity f of x a to the power minus 2 pi I. Now the kernel is slightly changed. This type of kernel also we can consider for solving this Dirichlet type problems. Okay, so 2 pi I xi x. Okay, so this particular integral equation represent Fourier transform, and its corresponding inversion formula is given by equation number 51. Now here of course at this moment we will assume that our initial temperature is in the Scott's class, what I explained you in the morning session. Okay, and Fourier transform of uxt I will denote it by u cap xi t. As I told you, we are applying the Fourier transform with respect to space variable, and keep in mind this x is not one dimensional now, x is multi-dimensional. So x is converted into now Fourier transform parameter xi, and Fourier transform of u I will denote it by u cap. And therefore if I apply the Fourier transform on uxt, that is the temperature function uxt, then as notation wise I will write u cap xi t. As I told you that we are applying with respect to x, therefore the second, that time variable we will keep as it is, we will carry forward as it is.
Because it is a multi-index, xi x is, there is xi is multi-index and x is also multi-index.
Yes.
So product is,
Product is of course
I am saying you have to say.
yes. Xi is multi because x is multi-index.
Yeah,
So
so
xi is also multi-index.
But in the integral you have minus 2 pi I xi x. So that xi
Yes, yes.
It is a dot product.
It is a dot product. It is, yes, yes. One in, yes, yes, you are right. Because now we are working in Rn now. It's not R. So it's a multi-index. X is multi-index. X is having suppose x1, x2, xn, n components. So our corresponding Fourier transform parameter also multi-index. Okay, and therefore you consider it as a dot product.
So here in the definition, you just say that.
Yes,
It's a dot
yes,
product.
yes, that product is there. Yes, correct. And notation wise, I will write here as it is. Even though it look like as a single variable, but it's not a it's not a one dimensional. It's a multi-dimensional now. And now I will apply the Fourier transform on the governing differential equation. So our governing differential equation is derivative of u with respect to t minus del u. Del is the Laplacian operator is equals to 0. Now I have simplified each and every step for the better understanding again. Okay, so as we are applying Fourier transform on both sides of the equation, or both term of the equation I should say. So okay, so this is the derivative of u with respect to t. We are applying its Fourier transform is that integral equation, and it's this 1 upon root 2 pi actually is a normalized coefficient. Okay, so here also I will have to apply uxx only I have written, but again it's a multi-index. Even though I have written as a uxx, but as I told you in the Cartesian domain, what will happen? This is a uxx. Uxx means all the variables, all corresponding components are under consideration. So keep in mind, this is we are carry forwarding this this multi-indexing is there always. Okay. So here notation wise directly, because we are applying Fourier transform with respect to x variable, so I will directly write this term as a derivative of u with respect to t, and this is under the effect of Fourier transform. Therefore instead of writing u, I will write u cap, and u cap is function of xi and t. Xi is a Fourier transform parameter. And here what will happen? Here of course I will have to simplify this equation as like what we did in the last problem, that integration by parts. So integration by parts means integration of the first term, that is uxx, integration is ux, second term as it is. This is free from integration now, and minus infinity plus infinity, minus integration of integrated function, that is ux, and derivative of first. So this type of simplification I will have to do. Again what will happen over here? For the bounded net condition, that ux tends to 0 as x tends to infinity, right? So ux, that is the rate of change of temperature with respect to x variable, will tend to 0 as x tends to infinity, and therefore this first term vanishes. So remaining term I can rewrite, and I can apply again, once again I can apply integration by parts, because it's again ux, so it's integration is u. First term will be as it is, this constant coefficient I have written outside, okay, and integration of integrated function and derivative of first. That way, that normal mathematical calculation I have done over here. And again, for the bounded net condition, this is under consideration, that u and ux tends to 0 as x tends to infinity, and therefore first term will vanish over here. So remaining quantity is this. Now what will happen over here again? So this integral equation along with this constant coefficient 1 upon root 2 pi will represent the Fourier transform of u according to our original definition of the Fourier transform. This coefficient I will write 4 minus, of course I square is there, minus 4 pi square z square and u cap. Okay, so this equation can be rewritten like this, and now you can see this problem is shifted to the ordinary differential equation. Originally it was a partial differential equation. This is shifted to the ordinary differential equation, and its boundary condition also directly I can write over here, because u at t equals to 0 is fx. So u cap at t equals to 0 will be corresponding Fourier transform, that f xi, right? I can write it. Go ahead. Now next. So once we solve the corresponding that ordinary differential equation, here directly I have written, because it's unknown coefficient, and unknown coefficient is nothing but that initial condition. The similar calculation what we did in the last problem. Okay, so solution of the last ordinary differential equation what we have been achieved is given by equation number 52. Okay, but still this solution is in the Fourier transform domain. we'll have to shift it in the our original domain, that is xt, and therefore I will have to apply inverse Fourier transform. So inverse Fourier transform here, I will apply inverse Fourier transform on the both side of the equation. Notation wise, we have written here that u cap represent the Fourier transform of u. Therefore, inverse Fourier transform of u cap directly I can write as a u, and xi parameter I can shift it to the original x. Okay, but here again it's a product of two function, and as it is a product of two function, I will have to take the separate Fourier transform and their convolution according to the property of the Fourier transform. So I will take the convolution of the first term, inverse Fourier transform of the first term, that is f xi, and inverse Fourier transform, that is exponential function a to the power minus pi square, 4 pi square and xi square, okay, and their convolution. So it's again notation wise directly I can write as f xi represent a Fourier transform of fx, so its inverse can be written as fx, and here I can write the inverse Fourier transform of this particular exponential term. I will call it as a ktx, and ktx again represent our hit kernel. Okay, so ktx nothing but the this particular term here I have written of course in the cap notation, because it's a Fourier transform of this particular kernel. Okay, so this will give us the solution in again the same form, that Poisson integral formula. The solution of the problem is again in the same form. Only this kernel will of course get changed according to the what type of boundary condition and what are the geometrical condition of the problem. Accordingly, this kernel will get changed. But again, the kernel is always a good kernel as t tends to 0. Those properties are again, everything is applicable. What I discussed in the last lecture, everything is applicable over here. Okay, so here of course kernel you can write ktx, or you can write it as it is a function of x and t. Okay, this Fourier transform is like in the last problem directly I can write it over here. If we find out the inverse Fourier transform of this particular term, so you will get this particular quantity, this particular expression. I have not solved it in detail because it needs a lot of computational skill in the and of course Fourier transform properties. So this will divert our area what we are discussing right now. So directly I have written its inverse Fourier transform is this particular quantity. So I will shift it over here, and this particular kernel is known as a Gaussian kernel or Weierstrass kernel, or in general you can call it as a hit kernel. Okay, and it has these few properties which are helpful to prove that this particular kernel is a good kernel. Later on we can, with the help of these properties. So this is the development of the Gaussian kernel, and of course this is what you can say again by applying Fourier transform you can solve a multi-dimensional problem too. But only thing is that, let me tell you a few things about this particular problem. Because as I told you, if it is in the Cartesian domain, then Laplacian operator is this particular quantity, that is double derivative with respect to x plus double derivative with respect to y plus double derivative with respect to z. Okay, so all these are the variable having similar properties. Their geometrical properties are same, and therefore for all of them I can apply a Fourier transform. But if we are working in cylindrical domain, or if we are working in this spherical domain, then this operator will get changed, and this operator will be shifted in another domain, that's cylindrical, or what you can say spherical domain. So that time you cannot apply at random Fourier transform for all space variable. So that is going to be again a little bit complex as compared to this particular problem. Okay, so if you are working in a cylindrical domain, then our domain under consideration is r, theta and z. Okay, okay, so in the cylindrical domain, so variables are under consideration. Laplacian operator is in terms of r, theta, z. Now here these properties, geometrical properties as well as physical properties of all these variables are different. So you cannot apply at random Fourier transform for all. Fourier transform, as I told you, the Fourier transform is applicable for the Cartesian variable, that is x, y, z. For this particular variable you can apply Fourier transform. Okay, but the property of theta and property of r is totally different. So you cannot apply Fourier transform. So for that, what you can do, actually basically our problem is now r theta z are the space variable and t is the time variable. So basically there are 4 independent variables as far as 3-dimensional problem is concerned. So 4 independent variables, and now we'll have to convert in terms of partial differential equation to ordinary differential equation, means I will have to convert into single independent variable. So for that I will have to remove all these 3 variables. So this variable can be removed with respect to Fourier transform. By using Fourier transform, this theta variable can be removed by Legendre's transform. Legendre's transform is also integral transform. You can see its definition and all those things. Okay, so by applying Legendre's transform over theta, you can remove the variable theta, and r variable can be removed by using Hankel transform, because Hankel transform is more suitable transform for the this r variable, because every transform has their own properties, and those transforms are convenient to apply to remove this type of variables. So at random we cannot use any transform to any type of variable. Time variable Laplace transform is suitable. X, Y, Z Fourier transform is suitable. R Hankel transform is suitable. Theta Laplace transform, Legendre's transform is suitable transform. So here we will have to use 3 different integral transform. To solve this particular problem, we will have to use 3 different integral transform and their corresponding inverses. Once you apply the Fourier transform of Z, you will have to apply inverse Fourier transform. Not directly. Firstly, apply all those integral transform and then apply one by one by the same sequence. You will have to apply, once you apply Hankel transform, then Legendre's transform, then Fourier transform, then you will get solution in these 3 domains, different domains. Its corresponding variables which get changed. Suppose this gets changed in xi, this will get changed in suppose psi, this will be something like chi. Okay, so these variables in this particular domain and t is there again. So in this particular domain you will get the solution. Then I will have to apply again all inverses. Inverse transform to remove xi. Now you will have to apply inverse Hankel transform. Then you will go back to the r. Apply inverse Legendre's transform. You will go back to the theta. Apply this particular transform. You will go back to the t. So these 3 transforms followed by 3 inversions. Then you will get the solution in terms of r theta z. Same thing is applicable in spherical variables. Spherical variable r is there, theta is there, phi is there, and t is always there. So for theta and phi you can apply Legendre's transform. As I told you, these are the convenient transform for this particular variable, and r again you can use Hankel transform. So this is the way that the choice of integral transform is very important to find the solution. But the advantage of this particular technique that you will get the analytical solution. Of course, there are also many limitations. Means directly for all problems you cannot say that you will get the analytical solution, because that depends on the so many other factors, non-linearity occurring in that particular problem, and all those things you will have to take care. So accordingly you will have to choose. But in most of the cases, once these transforms are applicable, then you will get the closed form solution, exact analytical solution. So this is the advantage to apply the integral transform for the boundary value problem, and the corresponding solutions are the exact solutions or closed form solutions you will get. So that's the reason this is the most popular method in the solution of particularly not only boundary value problem, but in the heat equation, even in the wave equation also you can apply this particular technique. Okay, so now let us go ahead. So this theorem is applicable, what I told you again, because every time once you design a particular problem, and it's when you are talking about the solution, of course you will have to check its well-posedness. The well-posedness is essentially required. Being mathematic person, we'll have to check the problem is well-posedness solution exists and unique and stable. So those conditions you cannot ignore. So again, being a hit kernel and the hit kernel is a good kernel, so this theorem, whatever I taught you in the morning session, this is applicable over here in the multi-dimensional problem too. So once again you can see this is written in the form of Poisson integral formula. Okay, so this satisfies this solution exists. Okay, this is a f is bounded, and whenever f is bounded and continuous to initial condition, it satisfies the initial condition. And now of course, as you were talking about the multi-index, so here better to consider LP space. Okay, and this convergence can be checked in the LP norms. Okay, so this is only the corresponding change we'll have to do. Otherwise, that theorem of the existence and uniqueness is directly applicable over here. The corresponding changes being a multi-indexing, of course, we'll have to take care that we cannot ignore. But by this particular theorem, you can check the well-posedness of the problem also. Okay. Now this is a big problem. Shall I go? Now I need your permission for that.
You can go ahead.
A little bit I will discuss.
No, you just-
So still I think 10 minutes.
10 minutes.
Yes. So one problem I will discuss before concluding this particular session. That's a very great problem in the unit disk. So unit disk is defined by domain D. It's a R theta. R represent it's a radial variable. Theta represent angular variable. Unit disk, so radius is 1. Radius varies from 0 to 1. Theta varies from 0 to 2 pi. C represent its circular boundary. This you can better understand. Okay, so C represent its boundary, that is R theta, R is equals to 1, as we are talking about this boundary, therefore its a circumference, radius is 1, theta varies from 0 to 2 pi. And here in the derivation problem in the unit disk, we will consider a steady state equation. Now steady state I have not taken, that's why I chose this particular problem. Okay, so del u is equals to 0. Del is, now we are working in R theta. So Laplacian operator in R theta is this expression. So second order derivative of u with respect to R, 1 upon R first order derivative of u with respect to R, and 1 upon R square second order derivative u with respect to theta. This is the conversion of Laplace operator in terms of R theta, polar coordinates. Okay, and steady state, so there is no means rate of change of temperature with respect to time is not there now. This is the first problem we are doing now for steady state condition. So rate of change of temperature with respect to time is not there because it's a steady state problem. And the condition imposed on the circumference of the circle, that the circumference of the unit disk, that temperature prescribed is f theta. As I told you, because R equals to 1 is fixed there. So temperature prescribed is f theta. Okay. So this is the mathematical formulation of the problem. We can solve this particular problem. Integral transform is not required here because I don't know how many participants are aware of the Henkel transform and Weissenreich transform. So I avoided that particular transforms, and I will use because it's a steady state problem, and therefore this separation of variable is applicable. So I will use this simple technique of separation of variable, and we will come to some solution and its properties, of course, later on. So separation of variable, as u is a function of r theta, and therefore u can be written as f of r and g of, it's a product of f r and g theta. F and g are the unknown functions. I can substitute in the original equation, and I can just simplify accordingly. So by separating variables once again, so I can reach to this particular equation, and this is the variable separated form. Here f is a function of r, g is function of theta, and as again theorem on equal ratios says that these two ratios are equal, then it must be equal to some constant lambda. I can solve these two equations separately. Okay, so this first equation I will use d square plus lambda of j operating on j theta is equals to 0. So I will get the roots like d square is equals to minus lambda. Now here g is a function of theta. Okay, and g is defined on circle, And as I told you in the morning again, if function is defined on the circle, the function is going to be a periodic function of period 2 pi. So we'll take the advantage of periodicity of that particular function. Okay, so go ahead. And therefore I can take when lambda is positive, lambda is equals to m square, m is positive integer, and then d can be written as of course plus or minus mi, and then g theta can be written as a cos m theta and g sin m theta, or I can write in the exponential form also. So this is the solution for g theta. Here once again let me tell you, the function is defined on circle, and therefore whenever we are talking about the function defined on circle, then that function is going to be a periodic function of period 2 pi. This is the you can better understand geometrically these things. Go ahead. Now if I consider this f function, and this is a Legendre type equation, you know, this r square into second order derivative of f, r into first order derivative of f. So this is you might have studied somewhere the Legendre type differential equation. Therefore this is not a constant coefficient, this is a variable coefficient, and therefore I will have to convert into constant coefficient by substituting r equals to some exponential function, that is a to the power z. Whenever I will put r is equals to e to the power z, then z is nothing but log of r. Okay, so if I calculate these quantities, this calculation I have not done over here, but you can do it easily. You can do this. So r square f double dash. So this will be shifted to this particular expression. Okay, and of course d represent d by dr, and the corresponding differential equation is like this. So this substitution will help us to convert the variable coefficient into constant coefficient. So of course the corresponding solution can be written in the exponential form, and of course z variable I can rewrite in terms of, that is log r. Okay, and e to the power log r, of course I will write r to the power m, because these are inverse functions of each other, and equation 61 will gives me what I can say f of r. So I got f of r, I got g of theta, and product of these two functions will give me u of r theta, and therefore this is the product of two unknown function f of r and g of theta. You can go ahead, and now our job is to find out all these constant coefficients. So firstly what I can say, as r ranges from 0 to 1, now as whenever r tends to 0, that d upon r to the power n tends to infinity, and then this case f will be unbounded, and therefore d must be 0. So I got d is equals to 0. The remaining variables, I mean constant coefficients c, a and b, I can write it as a single variable, as we done in the one more problem in the morning. Because here m ranges from positive integer, this is negative integer, so I can combine it as a all means integers only. Considering separately positive and negative separately, I can combine it and I can write it r to the power mod m, where m belongs to z, and e I can take it as a single variable. And as m belongs to z, so there are multiple solutions, so I can combine it by taking summation. So summation m minus infinity to plus infinity, am as a coefficient, r to the power m and e to the power m theta, where am is the arbitrary constant coefficient, and now I will have to find out this arbitrary constant coefficient. Go ahead. So this can be done with the help of initial condition. What is the initial condition? The initial condition is u is equals to f of theta whenever r is equals to 1. So I will put r is equals to 1, u is equals to f theta, so I will get this particular equation. So this particular equation is nothing but again a complex form of Fourier series, and therefore am represents the Fourier coefficient. But if you want to do by simplification, then again you can take the advantage of orthogonality property of the exponential function. You can multiply both sides by a to the power inx, okay, and you can integrate both sides within minus pi to plus pi. Okay, so that way also you can do, or directly as a being a Fourier coefficient also you can write as a expression for the Fourier coefficients. Go ahead. So you can simplify this equation, okay, and you can take the advantage of orthogonality property. And what is that orthogonality property? Whenever m and n are equal, then it's a 0, and whenever they are unequal, it's a 2 pi. So I can substitute over here, and then accordingly I will get value of constant coefficient am. So this is the constant coefficient am. Okay, so my final solution is what here go next. Okay, so this is our final solution, that u r theta represent temperature at any particular position r, and of course r theta, I mean to say r theta both represent position variable, and corresponding variable is this. And again I can develop the corresponding heat kernel by substituting value of am over here. What we did like, okay, so this am I can substitute over here. For better understanding only, I have changed the variable theta to pi. It does not make any difference. Okay, so I have changed the variable. You go ahead, and the corresponding equation I can rewrite in the form of convolution of two function again. If theta is the initial condition, and that remaining kernel, this summation is nothing but the Poisson kernel. This summation m is equals to minus infinity plus infinity r to the power mod m e to the power I m theta minus phi. So this represents the PR, where PR is the Poisson kernel. What is Poisson kernel? For your better understanding, I have written the definition over here, that PR theta is this is the infinite summation m is equals to minus infinity plus infinity r to the power mod m e to the power I m theta. This is the Poisson kernel. Poisson kernel is also a good kernel. Okay. So here this is same expression, so I have written it as a PR theta minus phi, and this integral equation represents a convolution of two functions. One of them is the initial condition, another them is the heat kernel, you can say, or specially we can call it, like last problem we call it as a Gaussian kernel, here we will call it as a Poisson kernel. Okay, and then again the same thing is repeated as we have written in this particular standard form, in the convolution form with the heat kernel. So as it is a good kernel, so all the properties of the well-posedness and existence and uniqueness is applicable over here. Okay, you can go ahead, I have mentioned over here same thing. Okay, so this is the Dirichlet problem in the this, and of course we have solved the various problems of the heat conduction, one dimensional as well as multi-dimensional, by separation of variable and also by integral transform technique. But at the end, that I have shown you, the solution can be written in this particular form, in the convolution form. Okay, and the first function represents the initial condition prescribed, and the second function represents a heat kernel. Okay, and again we can take the advantage that heat kernel is a good kernel at t tends to 0, and then the corresponding properties, and then we can prove this existence, uniqueness, and all those things. So this is about the various techniques of solving heat equation, one dimensional as well as multi-dimensional. Okay, so if you have any doubt, you please talk to me. Otherwise, here I will conclude this particular session. Okay. Any question? Thank you.